Hello there, welcome to the third of the live lessons, and slightly late tonight, so I'm going to get straight into it with the first question. And you'll see that I've changed the title, so I'm hoping to go through most of dynamics in space tonight, or at least as much as I can. So here we go, this is the first one. Now I've got a little bit of working up on the page. I'm going to get rid of that. That relates to a question that comes up later. And yeah, you can see it says on the screen, spot the vectors. So how many different things? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 of these. And I'm just going to give you a second. Of course, the kind of question you might be asked is the difference between a scalar and a vector. And of course, they both have magnitude, they both have size, but of course, the vector also has direction. So that's the difference between. So vector has direction, a scalar can be described just by its magnitude. Now, hopefully, when you've been looking at those, the ones that you have identified as vectors are the ones that come up here. And if I can find my pointer, so far we've got force, velocity, displacement and acceleration. We'll be doing some questions later, and I'll talk about the difference between distance and displacement, speed and velocity. But the ones which are highlighted in yellow, those are the vectors. Now, one I could have mentioned, so we've got force here, and just remember as well, weight. That's something else you could be asked about. Weight is, of course, a force measured in newtons, so of course weight is also a vector. But these are the main ones you would need to identify as vectors from that list. Okay, so nothing to write down there. As I said before, some of these questions you can be working through yourself with pen and paper, calculator. I wouldn't imagine there'll be too many people watching live just now because of course the main exams are coming up, and hopefully by the time that this is then uploaded to YouTube, then at some point when it's more convenient, of course, you can then find the PDF document of the questions on the website. Download that, have a look at them first if you want, and then try the questions. So we're going to go with the next question then. And you might want to write something down for this one. Here we have it here. Now I'm hoping that that graph is large enough for you to see. The question says, during a school sports day, a girl takes part in a sprint race. A graph of the girl's motion is shown from when she starts running to when she crosses the finishing line. And part A says, calculate the girl's acceleration during the first 4 seconds of the race. Now, here is the graph, and this is of course on the y-axis velocity in meters per second, on the x-axis time, and you can see in from 0 to 4 seconds on the x-axis, the velocity is going from 0 up to 8 meters per second. And then after that point, we have a constant velocity. So this is a straight line as well. Obviously not a constant velocity, it's an acceleration. One question is you might actually be asked to describe the motion. So for the first 4 seconds, we have a constant acceleration. From 4 seconds to 14.5 seconds, we have a constant velocity. Okay, now to answer that question, what we would need to do is of course use this equation here. A is equal to V minus U over T. Remember of course that U comes before V in the alphabet, so U is the initial velocity, V is the final velocity. I'm going to move that pointer out of the way. And of course you can see that after 4 seconds the final velocity is 8. The initial velocity at the start is 0, and of course the time it takes for the velocity to increase from 0 to 8 meters per second is 4 seconds. Now of course I'm not going to use the calculator to work this out. So this, as we said, is part A. So 8 divided by 4 gives us of course 2 ms to the minus 2. Now remember of course there is also a sheet which I have on the website, which is help with the relationship sheet, which just goes through all the different units as well, of course, speed, velocity, ms to the minus 1, acceleration, ms to the minus 2, and so on and so forth. So if you're having difficulty remembering some of the units and so on, and familiarizing yourself with the equations, then have a look at that. And of course, if you've done enough of these questions, usually what will be asked as well in a velocity time graph question is this. Now this is a show question as well. I've spoken about show questions before, in that you really need to make sure that you've got all your working in these questions. You're not missing any steps. Now, I guess you can see that the fact that someone's ran a race and it's taken 14.5 seconds is not going to be the marathon, it's not the 200 meters. Sometimes, well, of course, actually it does tell you, show that the distance covered by the girl was 100 meters. We actually know the answer. So what I would always do in these questions is, if we're finding distance from a velocity time graph, of course, what we're writing down first, I would always say, is of course the distance is equal to the area under the velocity time graph. And since it's a show question, then as I said, you really don't want to skip any steps. And in this graph at least, we're using the area under the whole graph. So just look out for some graphs where maybe it's only asking for the distance while accelerating, or it could be a car braking and you've got to find the stopping distance, or the braking distance I should say. Maybe you're only working at the area of one part of the graph. So of course in this question we have, for the first 4 seconds, a triangle underneath this line. We're working at, as I said, the area under the velocity time graph. So we've got this triangle here. We'll be working at half times the base times the height. And then of course we've got this rectangle with a base from 4 to 14.5 is of course 10.5, and with a height of 8. Okay, so we've got distance, as I said, is the area under the velocity time graph, and the first triangle, as we said, half times the base times the height. So half times the base is 4, the height is 8, plus the rectangle we said was from 4 to 14.5 seconds. That was the base, so that's 10.5 seconds multiplied by 8. And this is the important thing in a show question, that you obviously you don't want to say distance equals area under VT graph is equal to 100. We know that answer, but we're getting the marks of course for showing our working here. Now at this point I should be looking at the calculator, and let's see, that first part I'll work at each term separately. So 0.5 times 4 times 8 is 16 meters, plus 10.5 times 8 is equal to 84 meters. And of course 16 plus 84 gives us the answer we're looking for, which is 100 meters. There we are. Now of course there are other things which could come up in velocity time graph questions, but a lot of the time we'll be working out acceleration and of course the distance as the area under the graph. What I did want to show was one last question. Now it's not a fully formed question, not a very long, and if I can just look that up, it's this one here. So again, quite a small graph. Hopefully that shows up okay on your screen. The question says, a man takes part in a cycling race. A graph of his motion is shown for the first minute of the race. Label the diagram showing the horizontal forces acting on the man from 45 seconds to 60 seconds. Now of course why I'm asking this question is just a lead in to talk about Newton's laws. We'll talk about Newton's first 2 laws, and I have a question later about rockets, so we'll maybe mention Newton's third law. Now the important thing of course in this question is, if we look, and the question's asking us to talk about the forces between 45 and 60 seconds. And of course from 45 seconds, which is here, to 60 seconds here, we have a constant velocity. And that's always something we should be looking for in a graph, or mentioned in the question. When we read or when we see in a graph about constant velocity, of course we're thinking of Newton's first law, and we're thinking about balanced forces. Okay, now what I don't have is I don't have another diagram of this cyclist, so I'll just draw that by a box here. Remember, it's not a test, thank goodness, not a test in artistic ability, so we'll just draw that. Now, of course, if I'm drawing, now let's see how it was worded. Label the diagram showing the horizontal forces acting on the man from 45 seconds to 60 seconds. Name the forces and show their direction. So what I should really be doing, I'm going to move the paper, is, I'll just show you what I'm doing. I should be making sure, of course, that since we're talking about balanced forces, that the length of the two lines I'm going to draw is the same. So I'll draw a line here which is just 2 centimeters long. A line, in fact, we'll draw it from the box, 3 centimeters long, and from this end the same length. So I guess it's like a scale diagram, although I'm not, of course, writing down what my scale is. We'll go back to this view here. So of course this box represents the cyclist, and to the right we have a force, to the left we have a force. So of course, looking at the diagram above of the cyclist himself, of course the force acting to the left would of course be frictional forces. That could be air resistance, which could of course be called drag, friction between the wheel and the, or I should say the tyre and the road. So I'll just call that friction. And of course this force would of course be, we could just call that pedaling force or something along those lines, pedaling force. As I said, I could have added a little bit to save time. I've made this a very short question just so I could bring up the fact that could be, of course, in the question, when we're talking about velocity time graphs, there could be a part where a section in the graph where the velocity is constant, and of course that would be relating to Newton's first law. Okay, and of course Newton's first law, we're looking for balanced forces. So as I said, this line of course here would be exactly the same length as this one and in opposite directions. Okay, so these two forces are obviously balanced, and it could be a question asking you to describe the forces, and you'd be mentioning the fact that the forces, horizontal forces in this case, acting on the cyclist are balanced. Okay, so remember, of course, Newton's first law says that an object remains at rest or moves at constant velocity in a straight line unless acted on by an unbalanced force. So Newton's first law relates to balanced forces. Newton's second law relates to unbalanced forces. And in Newton's second law, we'll talk about that one later, there is an equation that's related to that one, and that's of course the relationship where the acceleration of the object, it's directly proportional to the unbalanced force. So Newton's first law, balanced forces. Newton's second law relates to unbalanced forces. Now, as I said, that's just a little lead into Newton's laws, and of course also I guess a lead into vector addition as well, because of course we're talking about two forces. Forces are vectors, and of course it's important the fact that these two forces here are acting in opposite directions. And here we go, we're going to find another question. As I said, this is to do with vector addition, and there we go. Now of course I will need a new piece of paper for this one, and we'll read the question. It says, during the first race of an orienteering event, a woman runs 320 meters north in 50 seconds. Stop shuffling the paper. So 320 meters north in 50 seconds, then a further 460 meters east in 70 seconds before reaching the first checkpoint. And the question asks, calculate the woman's displacement from the starting point to the first checkpoint. Now of course there are two ways we can work this out. I think the first way I'll do this, and it always helps to be able to do this both ways. Of course you will be given a choice, so the question would say something along the lines of by scale diagram or otherwise. Okay, so we'll do the scale diagram first, and then we'll do the otherwise. We'll work out the answer to this mathematically. Now if I'm going to draw a scale diagram, then of course it's important that I write the scale. And really what I want to do is I want the scale diagram to fit as much of the space as I can. The more, or the larger I guess I can draw the diagram, then the more accurately I can measure the resultant displacement. That's what I'm trying to work out in this case. So let's see, I guess I'm adding 320 meters north, then 460 meters east. What I could do, I guess, is if I was to make 1 centimeter represent 100 meters, then the length of the two lines I'd be drawing would be 3.2 centimeters and 4.6. That sounds a bit too small. So in fact, the scale I'm going to use is, and I would write that down, let's see, 1 pen at a time would do. Scale 1 centimeter represents 50 meters. So let's see, if that is of course the case, and we look at the calculator, first line I guess I want to draw is 320 meters north. Divide that by 50 using the scale, and of course that would then mean that I'm drawing a line which is 6.4 centimeters long. And need to, I guess, plan this out in your head as well, that I guess I'll be starting down at the bottom left, because of course I'm going to be drawing something upwards representing north, and then I'm going to the right because it was talking about force of 460 meters to the east. So let's see, 6.4 centimeters we said to the north, starting from here. I'll try and do this as quickly as I can, but as accurately obviously as I can. This is what's known as a component. I'm going to add 2 components to give me the resultant displacement. Now what was the other? It was 460. I will show you the question again. 460 meters it said to the east. Using our scale, then divide that by 50, and that would mean that we would have a line which is 9.2 centimeters to the right, representing 460 meters to the east. So from here, 9.2 take me to about there. Now what's important in these questions of course is that I'm adding these 2 vectors nose to tail. In other words, where one of these vectors finishes, the next one starts. Now this is a little bit easier in this question because of course it's talking about orienteering, and of course where this person finishes walking north, they then continue from that point. If you're doing a question say on forces where 2 forces are acting on a certain object, it might not be obvious from the question. In fact, the way that the diagram is drawn, it might not have the 2 forces acting nose to tail. So of course you would need to draw a diagram like this. You would draw one vector first, where that one ends you would then, from that finishing point of the first vector, you would then start the second vector. And I've not my calculator, there we go. So there we go. This of course is the starting point, and this would be the resultant displacement. I'm adding this 320 meters north. This of course represents 460 meters to the east, and with 2 arrows that's of course our resultant displacement. We can call that D. I can move back to my normal pen now. I guess what I should do is I should measure the length of this line using my ruler. I would say that's roughly 11.3. So 11.3 centimeters. And of course the scale I used was of course that 1 centimeter represented 50. So 11.3 multiplied by 50 gives me 565 meters. And of course the next thing I would need to do, as I said, this is the starting point. I would always measure the angle here from the starting point here pointing towards the finishing point. Usually the angles are drawn with a theta. This is theta, represents the angle, and of course where's the 0 of the protractor? Right there. Yes, I would say that was 55 degrees. So of course that would give me an answer of D distance D is equal to 565 meters at, now of course this is north. From north I'm moving towards the east, so that would be 55 degrees east of north. So we say of, we're thinking from, you know, it's 55 degrees east from north, because that's where we were starting. So 565 meters at 55 degrees east of north. Now if you've been told, of course, to write your angles as a bearing, now what you could have written is, of course we can write it that way as well, that D would be equal to 565 meters at, you could say, at a bearing of, and remember we don't write degrees if we're writing this as a bearing, and we need three numbers, so we couldn't just write 5, 5, we would need to write a bearing of 0, 5, 5. So there you go. One choice, as we said then, is to use a scale diagram. Second way, and remember if that was a little bit too fast, what you can do is we can wait until that video is on YouTube, look at that solution again, pause it at that point if you want to work this out by scale diagram. Second way, of course, we just need to sketch this diagram. So remember, this would represent 320 meters. Where this component ends, or this vector ends, we then draw to the east 460 meters. And I would always say to draw a sketch. Now remember, of course, if this is north and this is east, then we do have a right angle triangle. The two vectors I'm adding, the components, drawn with one arrow. This one's the resultant, drawn with two arrows. Again, this is the angle that I need. And I'm trying to find D. And of course, this D squared would be equal to 320 squared plus 460 squared. So of course, D would be equal to the square root of 320 squared plus 460 squared. Now I've not written the square root sign yet, but calculator on, 320 squared, I'll not show you what I'm doing at this point, just so you can see the question. I didn't show the question very long before. 320 squared plus 460 squared, so I've got that, and then of course take the square root of that answer, and it gives me 560 this time. This is a slightly different number. This will be more accurate, but the last method was still fine. The reason we got a slightly different answer the last time was, of course, just because of the, I guess, the inaccuracy of the scale diagram, but you are allowed some give and take, plus or minus maybe 10 meters either way. So 565, what we got last time, would have been fine because our working was perfect. So I've got so far D 560. Remember, this is displacement, so of course because it's displacement and that's a vector, we of course need an angle. So at this point, here's the angle. Here we're working out theta. Opposite theta is 460. That's the opposite. This, of course, this is the longest line in the right angle triangle. This is the hypotenuse. So this is the opposite, and this is the adjacent. So what links opposite and adjacent is, of course, the tan function. Now you wouldn't need to write this down, which is why I'm writing it in red. Of course, tan of that angle there, theta, would be opposite over adjacent, 460 over 320. So of course what we want is we want to find that angle. So therefore we've got angle theta is equal to tan to the minus 1 of 460 over 320. And it'll be no surprise, I'm not going to do the working, you can try this for yourself, no surprise that that does actually work at the same angle as we had before. And again, what you would want to do is to put these two statements together. It's not enough just to work out the actual magnitude or the size of that displacement and the angle. You would need to put these two together. So last thing, of course, and we said before there were two different ways to do this. So we could say that D is equal to 560 meters at 55 degrees east of north. Or, again, as a bearing, D is equal to 560 meters at a bearing of 0.55. And there we have it. Now that we've worked out these angles, we don't actually need to work out those again when we do the next part of the question. There is one last part to this question. That was only part A, of course. So part B, it will take me just a second to find it, is this one here. There we go. So what does it say? Calculate the woman's average velocity during the first stage of the event. Now what I could have said before, of course, is if you were asked before to work out the distance. If I go back to where we started, this diagram here, of course the displacement was directly from the starting point here to the finishing point. If we had to work out the distance, then of course we would just, because distance is a scalar, add the 320 plus 460. Now what does that give us? That gives us 780 meters with no direction. So distance would just be 780 meters. If we had to find the speed, then what we would do is take that distance of, as I said, 780 meters and divide it by the total time. The total time in the question is 50 plus 70 is 120 seconds. Okay, now we weren't asked that. We were asked to find the displacement, which is why we're using vector addition, and we were asked to find, in this case, the velocity. So it's saying calculate the woman's average velocity during the first stage of the event. So this would be the same, it looks the same equation as if we were working out speed, but of course when we're using V is equal to D over T, V rather than representing speed is now velocity, D is not distance, it's displacement. So what we have is a displacement of 560 meters, and as I said, we have a total time of 50 plus 70 is 120 seconds, and that is, of course, I'll go to the calculator in this case, 560 divided by 120 is 4.66 and so on meters per second. Now, what values were we using in that question? Were we using 320, 460? Actually, the times. What we'll do, in fact, in this question is we'll use two significant figures. Now, as I've said before, the number of figures you want to use, same number of figures as the data in the question that has the least number of figures. So that, of course, would be 4.7 meters per second. And however I wrote the angle before, I'll just write that the same way again. Okay, so remember, you were either writing at 55 degrees east of north, or you were writing at a bearing of 0.55. So I'll just say the first one. So at 55 degrees east of north. There we go. And as I said, you could have written 4.7 meters per second at 0.55. Right, sorry for that. We'll just go on to the next question. So, if I can just open that up. Right, now as I said, we've mentioned Newton's first law, Newton's second law. This is a question which, when we're looking at rockets, we're often asked to talk about Newton's third law. Not in this question, actually. When we're talking about rockets, it could be that we have to mention the fact that when the rocket's accelerating upwards, the rocket exerts a force on the exhaust gases, and then of course the exhaust gases exert a force on the rocket. So that's Newton's third law. Now there's a big difference between Newton's third law and Newton's first law, in that both the first and third law talk about forces of equal size in opposite directions. But of course Newton's first law, both of those forces act on the same object. So we have balanced forces. Two forces acting on one object in opposite directions with the same size. But in Newton's third law, We're still talking about two forces acting in opposite directions with the same size of force, but those forces are acting on different objects. Now, as I said, we don't have a question about this in this part, but as I said, when rockets are mentioned, then of course we could have something along those lines. We're asked in this question, however, to work out the weight of the rocket. Now, again, I mentioned this last time, that mass is the one, well, the units of mass, kilograms, it's the one unit where we have to include the prefix. So because we're told that mass is 143 grams, we need to change that to kilograms. Now we'd divide that by 1,000 to get that into kilograms, and that would give us 0.143 kilograms. We would look to the front of the paper to find the value of the gravitational field strength on Earth, and that would be 9.8. And if I can just work this out, let's see, 0.143 multiplied by 9.8, 1.4014. Now we don't want to write down all of those values again. We've got 3 significant figures here in the mass, we've got 2 in gravitational field strength, so we really want this as 2 significant figures. Next part of the question looks like this. Let's see, it's here somewhere. It is this one here. There we go. So, what's it saying? Calculate the upward thrust on the rocket during the first 10 seconds of launch. Now, this is the one where we would use, of course, the equation which is related to Newton's second law, which is about unbalanced force, which is F is equal to ma. Now, as I said before, the mass is converted to kilograms, 0.143. Multiply, now let's see, where's the acceleration? Yeah, the rocket travels upwards with an initial acceleration of 14 ms to the minus 2. So 0.143 times 14 gives us, quickly go to the calculator again, 0.143 times 14, 2.002. So 2.0 newtons. And unfortunately, far too many people would leave the question there. Now this is only the unbalanced force. Remember that if there was an upwards force on that rocket equal to 1.4 newtons, then we would have the weight acting downwards plus an upwards force of 1.4. That would mean we would have balanced forces. The rocket at that stage would be not accelerating but moving at constant velocity. This unbalanced force really just tells us how much larger the thrust force is than the weight. So in this case, this is the unbalanced force. In fact, if we had the rocket, again, just draw a box here. We've got the weight force acting downwards. Weight is 1.4 newtons. And basically, we've got the thrust acting upwards. And what this is telling us, that the unbalanced force is 2 newtons, is actually telling us that the thrust force is 2 newtons larger than the weight force. So, of course, what that means is that therefore the thrust would be equal to the weight force plus the unbalanced force, in this case would be 3.4 newtons. And if you imagine, of course, that the thrust was 3.4, it would be far easier if you were asked in a question like this to calculate the unbalanced force. So if you were told the thrust was 3.4, weight was 1.4, it would be very simple for you to then say that unbalanced force with 3.4 minus 1.4 is 2 newtons. We're just doing the same process, but in the opposite order. Now, I wonder if there's time for this next question. If not, as I've done before, I can work at this later. In fact, I think what I'm going to do is I'm going to go to the last question. There is a projectiles question, and just like last time, what I did was I made a small video just going over the one question I hadn't quite had time to answer. So I'm going to do the same again, and you'll see in the PDF document, if you want to download that, I will mention which question it is that I am skipping at this point. It will take me too long, but it will be going over at some point later this week. So if I can just open up the last one, and the last one, this one here, is relating to light years, which of course that light year the fact that it has year in the name, people get mixed up and obviously think that that relates to, well, it's a unit of time. Of course, it's not a unit of time, it's a unit of distance. This question is saying the distance from the Sun to the star Gliese 687 is 14.8 light years. Calculate this distance in meters. These are not difficult questions. Once you know how to do these questions, no huge problem. Of course, we're using the equation from speed's distance over time. Distance is equal to speed times time. Of course, we're talking about light, and the speed of light, you'll find that, if you don't remember, at the front of the test in the data sheets, it's equal to 3 times 10 to the power of 8 meters per second. And now what we want to do is multiply that by the time, and the time we're talking about is 14.8 years, but of course the SI unit for time is seconds, so we want 14.8 years in seconds. I'm going to work this out in brackets, so 14.8 each year, and we don't need to worry about leap years. Each year has 365 days. Within a day we've got 24 hours. Within each hour we have 60 minutes, and in each minute we have 60 seconds. So that should be us. A quick check maybe to make sure that you've included everything that needs to be included. So distance is speed times time. We've got the speed of light 3 times 10 to the power of 8. Time is 14.8 years. From years we've got down to days, 365 days in a year. Within each day we've got 24 hours. Within each hour we've got 60 minutes. Within each minute we've got 60 seconds. So yeah, that looks fine. Last thing, of course, is to calculate that. So 3 times 10 to the power of 8 multiplied by, we don't need to use the brackets, 14.8 times 365 times 24 times 60 times 60 is equal to, and that gives us a distance of 1.4 times 10 to the power of 17 meters. And I think that'll do us this time. Now, as I said, there was one last question, and just looking at what I've got written down, this would take a little bit too long. It was about projectiles, so there will be, at some point later this week, there'll be another short video just going over that one question. Just to remind you, you can on the website, there's a form where you can write in about points that you might find difficult. Now, the important thing about that form is, of course, it's completely anonymous. I don't find out any information from the people who are clicking the boxes, other than the information that they find tricky. And I know that projectile motion, I think the number one on the list so far is transistor switching. That's what people are finding most difficult. I think number 2 on the list is projectiles. So it is important that we go over that question. Okay, now as I said, I think we'll leave it there. So again, thanks very much for watching. Look out for that video later in the week, and other than that, we'll see you next time. Good luck with the English exam tomorrow.